So first of all, I would like to thank Lars for this very nice introduction, and it is indeed a challenge for me now to give this talk. When I was asked by Mark to give a talk, a short talk, I said yes. But I must admit that I didn't know exactly what I was saying yes to. So I realized along the time that it's going to be a challenge, but I think I will take the challenge. So what I want to do today is with this topic that I am presenting. See, my title is All But Frustrating When Quantum Materials Meet Topology. I tried to choose a topic that is very much related to what Lars was saying, the workshop that now is running. In fact, I have to say that it's my, I think, 6th time that I am participating in a workshop here at the KITP, and it has been always a wonderful experience to be here, to collaborate with other colleagues, to get new ideas, to start new collaborations. Indeed, it's really what we call in our community a think tank for new ideas, for new directions. So it's really reality. So many of our fruitful collaborations were starting here. And in fact, I have a very, very, I would say, deep attachment to KITP because in my first workshop many, many years ago, I met my husband here. So this is indeed very special. And we have 3 children. So it was, it was very good. So what I'm going to do today is, in fact, showing to you that 2 very different disciplines, as it is topology. This is a completely mathematical concept. And the second is quantum materials, which is a field of research in physics. These 2 disciplines, in fact, have grown together in recent years. And by growing together, what we have been able is to understand and even discover new states of matter that we would have never thought of before merging the 2 different disciplines. And so I hope that along the way of telling you about it, I can give you a little bit of the interest that we are having in doing this field, since now indeed it's getting this concept of topology, it's getting in many, many fields of physics, and we are learning, in fact, very many new effects and new states that we didn't know before. The way I will present, so maybe I should say something about the illustration. You may think of why did she show such an illustration? So this is, in fact, basketry. And what I'm trying to show here a little bit is the concept of entangling different, so in this sense I'm using basically these pieces of straw, entangling different fields. But there are patterns here that you will recognize along my slides. So this was a little bit the motivation of putting this slide. And the way I would like to present these concepts is a little bit going back to history. So I will do it historically. The oldest concept is topology. So starting with topology, then showing to you how quantum physics was born and was as out of necessity. I mean, it's always the case that you have a puzzle. It seems at some point that the puzzle is, everything is working, but then there is this piece that doesn't fit the puzzle, and it may be that you have to reconstruct the puzzle again. So this is how we see physics and research, that you are all the time doing puzzles and trying to fit the pieces, but at some point, maybe you have to think again and start the puzzle from a very different point of view. And then, of course, I will go to, in fact, how these 2 fields have been growing together. So let me start with topology. The word topology, this is a Greek word made of topos, which means place, and logos, which means reason or study. And topology, what it does, it studies the properties of geometrical objects, take any geometrical object, that are preserved under what we call continuous deformation. So by, let me see if I had, so stretching or twisting, this kind of changes that you may do still preserve the properties of this piece of gum. And now you will ask, okay, what is that good for? So let me show you an example. Let's assume we are given this set of different, basically these are objects, and we are asked to bring them in groups by relating those that can be transformed one to the other by making deformations, continuous deformations, as what I'm doing here with the gum. So basically, if you look at the objects, they look very different. And what is important now is that we are not going to look at the details of the object. I'm just going to deform them and then see how many groups I can do. So if we do that, we can make, in fact, 4 groups. Let me start by taking the ball. So if I just press the ball, I can make it into a ball. So this would be one set. The second set is I can put the cup together with a donut because I can transform the cup. As you see, imagine that it's plasticine, so you can make, in fact, one going into the other. What about here, this pretzel? This pretzel, in fact, I can just see it as glasses. Basically, you have these 2 holes, so these 2 belong together. The deformation of one goes to the other. And the third one is this third pretzel. And now what is important is that you see that I can now, whenever you do a classification of whatever objects, in this case our objects, you want to define what is characteristic of each of these sets. So that's what we call this genus, which we also call topological invariant, which in fact is just counting holes. So if you look at this ball, this set, there are no holes. So this would be, in fact, would have the value of 0. If you look at this set, you have 1 hole. So this would be value 1. If you look at the set here on the bottom, has 2 holes, it would be value 2, and this one has 3 holes. So, and now, if you want to go from one to the other, either you have to take the scissors and do something really beyond a continuous deformation. So here you eat a piece of this pretzel in order to make it these 3 holes. So this would mean to really do something very drastic to go from one set to the other. So what is the key point about topology is that you keep the properties by deforming, and you can't relate the different systems by just making these continuous deformations. Now you can ask, what's that good for? Okay, I made these sets, very nice, but what's that good for? So let me show you some examples following a little bit the history of topology. So let me show you this one example. And this is an example that is very known in Germany, where I am now, since this is called the riddle of the 7 bridges of Königsberg. Königsberg used to be a Prussian city situated between now Poland and Lithuania, so in the Baltic Sea. Nowadays, this city belongs to Russia. I think its name is Kaliningrad. And the riddle is the following. So this city is crossed. So this is a map of the city, and it's crossed by this river. This is the Pregel, the river Pregel. And you see the way it crosses, and there are 7 bridges that connect the different pieces of the city crossing this bridge. And the riddle was, which I'm talking about here, the 18th century, whether it was possible to devise a walk through the city by crossing each bridge exactly once. So you had to construct this walk, and you could only cross the bridge once. So now, if you look at this problem here, it looks rather complicated. So where do you start? You start to think about possibilities. So here is where I'm going to use topology to solve this problem, and it will, as I hope, to convince you that the solution will be very simple. This is what Leonhard Euler did. So what I'm going to do is I'm going to abstract all the details of this map into very simple, what we call a graph, which is in fact a topological object. So what I'm going to do is every piece of land, I'm going to represent it just by a point, or a vertex we call it. So now I have how many pieces of land? 1, 2, 3, 4. And these are 1, 2, 3, 4. And the bridges I'm going to represent the bridges just by connections between these pieces of land. So I have these connections going from the A to the C, so it's going to be 1, 2, you see it 1, 2, and then through these are the connections that I'm going to use. So this complicated map now gets reduced to this graph. So let me just bring it back down here. And this graph has this vertex, which correspond to the pieces of land, and the connections in between the vertex, which correspond to the bridges. And now we can start solving. So this is now my representation of the problem, and now I can solve the problem. So the question is, if I am only allowed to cross a bridge once, it means that at reaching each point, so reaching its piece of land, I will need one bridge to go to this piece of land and another bridge to leave this piece of land. So I will always have one bridge going in, one bridge going out. So that means I'm going to have always, I have to have an even number of connections to one point, because I can have maybe two bridges going in, but then I need two different bridges to get out. So that means that if I want to do this kind of work, I should have an even number of connections coming to this vertex. And now you look and you have an odd number of connections. So therefore, there is no way to devise this work. So this is an example to show you how this topological concept, so of course you can deform, you can do whatever you want, as far as you don't cut a line, and cut a line means destroy one of these bridges, so then you would do something really severe to your city, the topology of the problem remains the same. Okay? So this is an example of how useful is topology to solve, for instance, this is a problem solved in the 18th century. Let me show you, if you have questions, just stop me anytime. So, no questions?
Yes, doesn't it matter where you start?
Okay, thank you very much for the question. Let's assume, so there are, this problem you can make it more complex. You can say, okay, let me assume that I start at one point and I end at the other point, or let me assume that I ask you, no, I want to go back to the same point. So if I assume that I start at one point and end at another point, then what is important is that the points where you are not starting and ending, these should have an even number of connections. And you see, whatever you take as starting and ending, the other two have always an odd number. But thank you. Yes, this is important. So this was an example. Let me show you a second example, which are knots. Knots are also topological objects. And in fact, also in the 18th century, it was van der Monde who already did connections of knots being topological objects. And humankind has always been fascinated by knots. So here there is, in fact, a Celtic knot which was found in the Book of Kelts. So this is 18th AD. And the topology of these knots, of these knots, has been coming along the centuries, and also the use of these knots. But let me, at least, again, by using this concept of continuous deformation, define when we call two knots to be equivalent. So two knots are equivalent if we can transform one to the other by making what we call a deformation in 3 dimensions. And let me take my how do you call that?
Rubber band.
Rubber band, thank you. So my rubber band, and you see what I'm doing from the A to B, I'm just doing this continuous deformation, so continuous 3D. So therefore, these two knots are equivalent. However, to make this one knot here, I should cut my rubber band and then start doing something different to get this C knot. So again, I can make a construction of knots by considering this continuous deformation. And let me show you maybe this is a movie because I cannot do that. So you see the knot, this knot indeed is equivalent to this knot here, because you can, by doing this deformation in 3D without cutting the rubber band, you can get back into this A. So knots are topological objects, and now I'm going to show to you, in fact, that knots have already, so there was a first encounter of knots in physics, in fact, in the 19th century. And let me tell you the story, because I think it's a nice story that very nicely presents how different fields, when scientists talk together coming from different fields, you can bring something new, in fact, some new ideas in order to get forward in what you are investigating. So here is, this was, whoops, pardon, this, so Peter Tide, he was a Scottish mathematician, and at the time he was very interested in understanding why, if you make rings of smoke, in fact, you have certainly observed that you make these rings of smoke, and they remain rather stable, and in fact, even propagate for a certain time without changing the shape. Right? So these rings of smoke, at some point, of course, they disappear. But you can keep stability of these rings during a certain time and also a certain displacement. So he was doing these experiments with smoke and trying to find out the reason why they are so stable. And he was discussing with these other also very well-known physicists, William Thomson, later on Lord Kelvin. He was discussing about the stability of these nodes that are, in fact, vortex of smoke. So at that time, William Thomson, we're talking about the 19th century, was very much interested in what is matter made of. This is more now my subject. So what is matter made of? So it was, at that time already, one was talking about matter is made of atoms. So in fact, if we go at very, very small distances, there will be the atoms that form matter. But the question was, what are atoms made of? So this experiment, this stability of these rings, gave William Thomson the idea that perhaps atoms, what they are knots of swirling vortices in ether. Let me tell you what's ether. I don't know whether you've ever heard of ether. Probably yes. So ether was was a medium that was postulated in the 19th century in order to find. So there was at that time unconceivable that light could propagate in vacuum. So therefore, when you don't have something, you just postulate, okay, there may be some medium where light should be propagating. And this was postulated that there should be a medium, and it was called ether, where light would propagate. And ether was then being used for anything, so any explanation that you couldn't find a better one. So basically, we do that many times. So it's not only in the 19th century, we do a lot. When we don't find a better one, we try to invent new things. So basically what he said, okay, seeing this very stability of this vortex, we could probably think that atoms are not, in fact, of swirling vortices in ether. And talking with his friend, Tide indeed started to make a table, so to classify knots, which is now a very valuable table, because this is being used in math, in fact, to understand knots, the difference, so depending on the crossings. And then they started to make a table of the atoms. So we should start with the simplest one. This was hydrogen, so the simplest knot. Let's continue with carbon. This is this tripod, famous tripod knot. Then oxygen, and so on and so forth. And you would build, in fact, matter by bringing these knots together. So this was beautiful, and this would explain also the stability of materials. This was beautiful, everything was working. We were at a stage where with ether we could explain all the world, but in 1887 in Cleveland, Michelson and Morley, they did an experiment. This was a very important experiment where they showed the inexistence of ether. And how did they do that? So this is, as far as I could find, this is indeed the original. They did that with an interferometer. So the idea was the following. So if ether exists, if this medium where light propagates exists, we have to think that we are in the Earth. So we are in the Earth, which is moving around itself and around the sun. So therefore, if ether exists, it should be possible to measure what was called ether wind. So that means the relative changes because the Earth is moving with respect to this medium. And therefore, the idea was, let's measure, in fact, how the velocity of light in two perpendicular directions, because then I will be able to measure this ether wind. And that was the experiment. So it was a very nice idea. They did the experiment, and they measured there is no difference. And this experiment has been reproduced 1,000 times, so there is no ether. This was good because it gave way to the theory of relativity of Albert Einstein, and all other this also for atomic physics. It was telling us knot theory is not here, so we cannot explain the atoms by using knots, even though, as we will see later, knots are going to be very important in physics. So therefore, we had to think about a very new way of describing the world at the microscopic level. And this is when we come with the quantum revolution. So it was the birth of the quantum mechanics when we are trying now to, we are trying to understand this microscopic world. And I'm talking about, when I put this number here, 10 to the minus 8 centimeters. So let's think this is a centimeter. And now you make 100 million divisions of your centimeter. And I'm interested in one of these divisions. So it's really, we are at very, very small distances. So in fact, then, what are atoms made of? And atoms, in fact, here I'm showing Bohr. We started to then talk about the elementary particles. So atoms are made of this nucleus of protons and neutrons, and then the electrons. And what is important now is that we are describing our world in terms of these elementary particles. Okay, protons and neutrons, they are formed by quarks, and quarks are together with bonding by gluons. But I'm going to show to you that, in fact, in quantum materials, we are mostly going to be interested in these electrons of the atoms. And what is important is that it was being done a very new physics. So Newton physics was showing to be here not right. So one had to develop many, many concepts to understand our microscopic world. So for instance, the electron, this elementary particle that is responsible for many properties of our daily life, it's an elementary particle that has a mass, has a charge, and has a spin. And this concept of spin didn't exist. This is it's an intrinsic angular momentum. And what is now, that's now here very, very specific or basically from the quantum world, is that it is quantized. So basically the spin of an electron is a spin what we call 1/2. It can only have two states. And this is also what characterizes these particles as what we call fermions. So we have fermions and we have bosons. And fermions are particles that they don't like to be together, while bosons, they like to be together. This is a very, I have to be very careful in using these words but basically this spin is describing the nature of this particle. And this was in fact Enrico Fermi, so it's what we call the Fermi-Dirac statistics coming from this spin. So we start to have concepts that were not there in the 19th century, and we're going to use them for describing our quantum materials. Moreover, this microscopic world, as I was telling to you, we cannot anymore use now Newton physics. So we are we are used to describe our macroscopic world with Newton physics, and it works very well. But as soon as you go to these microscopic distances, this is not anymore valid. So that now we are going to describe the kinematics of these particles in terms of, in fact, a new wave function, the Schrödinger wave function, and we are describing, in fact, the probabilities of finding our particles somewhere in space and time. So these concepts have needed almost a century, so the 20th century, to really be digested, to really be, indeed, there was a lot of discussion between, and let me show you here one of the famous meetings of, there were physicists, mathematicians, chemists, all together in order to describe these very new concepts, this quantization of many, so energy of, here for instance it was Planck, of angular momentum, as I was showing to you. So it's a completely new physics that is being developed. So that's why I left for the moment topology for some slides. And what I want to show to here is that places like KITP, where from all over the world scientists come to meet and discuss, are extremely important, because it allows us to really take some time and discuss about what is going on, problems that we have in our fields of research. So this is the Solvay conference, which was held in Brussels, and this is Ernest Solvay. He was a chemist, industrialist, who was funding, in fact, these type of conferences, and I think that they are still going on, but this was the first one. And maybe I just want to tell you here one interesting aspect about doing research. So if we think about the way the research, so scientists have been communicating along the centuries, let me just stay now here. I'm in the 20th century, it's not that far away, and I had the opportunity to read, so this is in Frankfurt in the university archive. There are some original letters between Albert Einstein and Max von Laue. Max von Laue was a professor at the University of Frankfurt for some years. And here I'm just putting some letters that I read, and this was when Albert Einstein was in Berlin, then in Oxford, then in Princeton, so between 1926 and 1936. And you see when reading these letters and when looking at the dates that it takes a long time till you are thinking about the problem, you write the letter, you send the letter, there are some weeks until Max von Laue was getting the letter, was thinking about the problem, writing back the letter. So we were having really long periods of time in the communication, and nowadays it's like you send an email in 1 second, you send your papers, you put them on the web, in 1 second everybody knows this. So we are changing a lot the way to communicate. So I just thought it was interesting. So as I was saying to you, and many of these letters, in fact, are related to the interpretation of quantum mechanics, of this very new description that was not there in the 19th century. So we're now, though, in the 21st century. So we have had enough time and not enough discussion, experiments getting better and better to really now have a very ripe theory. And this is, so quantum mechanics is now, we're using quantum mechanics for many things. And we know how to use that because there was a history of dealing with these new concepts that now are established. And now it's where I come. So now we can talk about quantum materials. In fact, I'm just putting here a piece of iron, and you will ask me, why do you call it a quantum material? A piece of iron has been there forever, for centuries. So why do we call it now quantum material? And the reason is because with all this knowledge about, in fact, what is this piece of iron made of, so I have in a piece of iron, so if I take a cubic centimeter, I have of the order of 10 to the 23, so you multiply 23 times 10 of electrons interacting. So what I want to say is that we call it quantum material because the properties that we see in this piece of iron are a consequence of these interacting electrons. So we can now understand the macroscopic manifestation of these interacting particles in the micro world. And what I want to say here is that in these interacting particles, what is important is if I just were to take an electron, then the next electron, and just look at these electrons and add them, there would be no way that I can predict what kind of behavior this piece of metal, in this case, is going to show. So there is, in fact, what we are calling emergence of distinct phases of matter that comes from the collective action of all these interacting particles. And what do I mean maybe by emergence, to give you an example, is let's assume you have birds. So you have birds, you see one bird, two birds, three birds, and you will never think that they are able to make these flocks, these very beautiful flocks that you see, in fact, in the sky. And this is a consequence. This is what we call emergence. So if I want to do a definition, that the behavior of the collective is not foreseeable from the knowledge of each of the constituents. And this is what happens in quantum materials. From the knowledge of just adding one electron and one more electron, there is no way that I can predict the different, what we call phases of, that there will be superconductivity or magnetism, all these phases of matter. So what I want to show to you now is to talk a little bit, because now I'm going to catch with topology again. So as you saw, I left topology in the 19th century, then I went to the 20th century and focused on quantum physics. Now we're in the 21st century, let's now bring the two together. So this is what I'm going to show is, okay, so I'm talking about emergence of phases, right? So that we have all these electrons interacting in these materials, and suddenly I have superconductivity, or I have that the system is a magnet. So therefore, the question is, how do I distinguish between these phases and understand them? And as usual, as also zoologists do, we try to find a criterion to classify and to try to see how I go from one phase, or from being magnetic to non-magnetic, superconductor to non-superconductor. And this is, in fact, symmetry. It's very important in quantum materials to be able to classify and understand different phases of matter. So what is symmetry? So symmetry is the invariance of an object under a given transformation. So, for instance, so if I look at, do I have a squared? Oh, I can show it here. So, for instance, this squared, if you rotate it 90 degrees, it remains the same object, right? So therefore, you would say this piece of this square, this cube, is symmetric with respect to a rotation of 90 degrees. Also 180 degrees. So you can do all of these symmetries, apply these symmetries, and the object remains invariant. If you do the same type of operation in this object here, you will see that if you do this 90 degrees rotation, you don't reproduce the same object, right? Because you do like that, and because these distances are different, you're going now to have a different, so the object doesn't go back to its own, basically to itself. So by doing this game of applying symmetry, and not only what we call this is spatial symmetry, so if I have this piece of iron and I apply symmetries, but also in the spin space, this spin that I was telling you about the electrons. So by using this concept of symmetry, we can, and I will show you an example, we can understand phases of matter. But now it comes what we call the new way, topology. Topology, this concept that I was showing to you at the beginning, that I can, in fact, define relations between objects by doing continuous reformations, I'm also going to use this concept to describe phases of matter. So let me show examples of this one, and then let me show examples of this other one. So here is where topology comes in again, in the game of physics, let's put it this way. So let me start with one example. Okay, so I should mention that it's very important is that these three physicists have been, so David Fowler's, Michael Kostelis and Duncan Haldane, they have been pioneers indeed in using the language of topology, so in bringing topology to the description of our quantum world, so in quantum physics. And they got the prize, the Physics Nobel Prize in 2016. So let me do now what I was telling to you. Let me then define a phase, a change of phase by using this concept of symmetry changing. And what I'm showing here is this is a liquid, consider water, and this is a solid, consider, for instance, ice. But here what I'm showing is just so the pictures, so water and ice. So now if we if I lower the temperature, you know that if you lower the temperature of water, you will go to, at some point, the water will become ice. Okay? So how do we describe this type of changing from one phase, water, to the other phase, ice? So if I look at the basically what is the constituents of this water and ice. So here what I'm showing is, let me go now at the microscopic view. This would be water. The water molecules are indeed disordered. Disordered in the sense that there is no, they basically, if I look from the point of view of symmetry, there is no symmetry broken, because on the average, a molecule of water sees the same molecules of water around. So you have here a symmetry. Now you go down in temperature, and what happens when you go to ice is that the molecules of water are going to order in a very, very well-defined way, because they will form a crystal. So you are breaking this continuous translation and rotational symmetry that you have here. So by breaking the symmetry, by changing the symmetry of your constituents, you can now describe the solid. So I'm describing now, and this is our classical way of describing phase transitions, some phase transitions, is by changing the symmetry of my constituents while going from one phase to the other. And a second example is, let me, instead of using now the spatial symmetry, I'm going to use the symmetry of the spins of the electrons. So if I have, here I'm calling a paramagnet, so if you have at very, very high temperatures one of these metals, they are, in fact, there is no magnetization, and we can understand that this spin of the electrons is basically disordered. So the temperature is so high, there are so much energies that they are basically disordered. So you have, on average, there is no direction of the spins. However, you lower the temperature, and at a certain low temperature, when you took out, in fact, all these thermal energy, they order. And they form what is a ferromagnet. The ferromagnet, if you look at in the microscope, it means that you are basically ordering the spins, and they follow, as you see, a pattern that it's what we call long range. So you can follow a well-defined pattern of ordered spins. And here again, you had rotational symmetry on all sides, and here you broke it, because you see it's not the same here, the same symmetry that's done here. So again, by using the concept of changing the symmetry, you go from one phase to another phase. Yes, sorry.
On the lower diagram, if you cool the material, must the electrons align in the same direction?
No.
So
no.
that's
so
only a specific case.
Exactly. So that's why we call it spontaneous breaking of the symmetry, and now it has many orientations. It can go like that, like that, like that. You will have many possibilities. It will choose one. And that's why we say we break the symmetry, because it chooses one. So if you put, so basically you can have this, but you could also have this, or you could also have, you have all these options. It's going to choose one.
And they will always be aligned.
Yes, they are always aligned. And in fact, the way you measure that, you put a very small magnetic field, and then you see very nicely this state. So this is what we call ferromagnets, that you have all the spins are aligned in the same direction. I will show you there are also the antiferromagnets, when you have that they like to align this up, this down, this up, this up. You also have this kind of state in some other systems. Okay. So this is now basically what we call a change of spin rotation symmetry to when we go to this ferromagnetic state. However, already in the 60s, from the last century, there was some problems in the fact that if you were to assume that you have, now let's consider you have a thin film, okay? So we call it two-dimensional system because it's basically a thin film. And what one would find out that when you consider these very special systems, there was no way to describe this kind of phases by changing the symmetry. And let me show you what I mean by that. So you know very well, I have one and probably many of you have one. So a hair swirl. So I don't know whether I pronounce it properly, swirl. So let's look at this, what is that exactly? So if you look at that, and this is, I'm doing basically the two-dimensional projection, you see that there is no way that I can define a symmetry of this. So you see it looks like a vortex, right? And I cannot define a symmetry. There is no 90 degrees rotation, not 120 degrees rotation, no translation. It's a very different state from what I was showing to you. So in fact, this kind of stage, we also have them in the microscopic world. And let me show you now, let me try to convince you that this is a topological state. So in fact, we call it this, as I will show it to you, it's basically a state that I can understand by using the topology concept. Okay, you can already see here that this is most probably a topological object because you see that whatever continuous deformation you do, so you try to brush it always stays the same. There is nothing that you can do unless you cut your hair 0 and then it's gone. But otherwise it's always, so any continuous deformation will remain the state the same. So we have exactly the same pattern in the microscopic world. So now I'm going to my spin system. So I'm going really at these distances, and if I have very two-dimensional system of spins, I have exactly the same type of vortex. And now what I want to show to you is we can use topology to classify the properties of this vortex. So let me show you this one here, which looks like the one that I was showing from the hair. And you see this, what I'm showing with this arrow is the direction of the swirl. And so we call it, this is a 2-pi winding, so it winds in this direction. So I'm going to give, if you remember at the beginning I was talking about this topological invariant that had these discrete values, 0, so when I was talking about, for instance, number of holes, 0 holes, 1 hole, 2 holes, you cannot have half a hole or a third of a hole. So these are always discrete numbers. So the same, I can classify this vortex through this winding as 1. Now, of course, you can have a different kind of vortex, and this is the one here. I try to, so the winding is just the opposite. And if you now, and this is an anti-vortex, which has a G number of -1. And there is no way, by continuously deforming this vortex, that you can get this vortex here. So these are two topological objects that you cannot transform one to the other. They belong to two different classes. So this is now the question whether, and we know in spin space, so in the microscopic world, we do have this kind of states. The question is, can I have now a phase transition like I was showing to you in the case of symmetry, I was changing a symmetry. What would be here the equivalent, because I have no symmetry here? So the equivalent is that, and this is what Kosterlitz-Taules, in fact, very nice work, and Berezinski also independent of them. In fact, you can, the only way to go into a new state is that you pair the two vortex. So you pair these two vortex and you come to what we call a paired vortex-antivortex, and this is a new phase of matter. This is the so-called Kosterlitz-Thouless, so it's a Berezinski-Kosterlitz-Thouless phase transition. It's very difficult to observe experimentally because you need these very nice two-dimensional systems, but this is a phase transition that has nothing to do with symmetry, and where topology is telling us, in fact, how to describe this phase transition. So, in other words, what I want to say is that topology helps us to understand phases of matter that there was no way that we could sort of describe them or even predict them. So now let me show you that I can find states, topological states, in fact, in our quantum materials. So, of course, this is minerals, but minerals are formed by electrons, and in fact, they have very special behavior, as I will show for one of those. And I can show you that we understand now how to describe this special behavior in terms of topological concepts. So this is Herbert-Schmidtite, Heideite, capelacite, barlovite. These are beautiful minerals. They have these colors. You see green, blue. The color comes because these are all insulators. So insulators means there is no electron current. And the color comes from the energy gap between, let's say, the states of the electron and the energy that you would need to make a conduction. So they have a gap of about 1.52 electron volts, which corresponds. So that means if you have an insulator, you have a gap, and light, you shine light. So basically, you will see it like transparent because it won't get absorbed. It will go through because there is a gap of energy, so the light goes through. And the color of the light depends on which is the range of your gap, right? So if the gap is between 1.5 and 2, the color is this blue that you see here, green. So that's the color of these minerals. So these minerals, they are very beautiful, but they also have very nice and very unexpected type of physics. And this is what I would like to show you in the example, for instance, of Herbert-Schmidtite. And the concept I would like to show, so the topological phase that I don't know how I'm doing with the time. You have to tell me.
2 or 3 more minutes.
2 or 3 more minutes, okay. You have to tell me.
Whatever you
So otherwise, you want me to start, you have to tell me, because I can tell you many. Okay, so let me continue. Let me show you at least in my last minutes what kind of, maybe a little bit more of 3 minutes, 5 minutes. Let me show you what kind of state now these beautiful minerals, in fact, we are discovering in them. And this is the spin liquid. And now you will say, a spin liquid. It's not a liquid of spins, but this is a word that is historical. Let me try to explain a little bit what it is. Okay, so in order to explain that, let me now take, instead of ferromagnet, I'm going to take an anti-ferromagnet. So this is, I'm going the wrong direction. This is this material. So this is a piece of this material that I just took it from. I'm not experimentalist, so I take the photos from my colleagues. This is lanthanum 2, copper 4. This is a ceramic system. And this ceramic system, this is an insulator. And at low temperatures, it has this phase transition that I was showing to you from paramagnet to an antiferromagnet. So it's an antiferromagnet. What do I mean by antiferromagnet? I mean the following. So if I now boil down this piece of material into which are the constituents, are these beautiful pictures here where I have copper and then the oxygens around the copper and then the lanthanum in between these copper planes. And what is important now is that the electrons we're interested in are the electrons of the coppers. We have 1 electron per copper. I'm simplifying that, but basically that's what I'm showing here. And these are the ones that are responsible for the antiferromagnetic behavior, that the system is going to go into this pattern. So what happens? I go down in temperature, And due to the interactions between these coppers, spins of the electrons like to align anti-parallel. So you see that I can nicely make this alignment without any problem. So up, down, up, down, up, down, and so forth. So I'm getting, indeed, this is what happens in real life. You go down in temperature, and the system orders and forms this antiferromagnetic state. So you measure magnetism, and you get the information that it is antiferromagnetic. So this is what we call the classical paramagnet antiferromagnetic phase transition. And maybe just to mention something, that these ceramics are extremely important nowadays, because when you dope then a little bit with strontium, these materials become high temperature superconductors. So these are the famous high temperature cuprates. But what we call the parent compound, this is an antiferromagnet. Now let me do the same game for a system where I don't have a square lattice. Like here I had a square lattice of coppers, of spins, and I could very nicely place this up and down. Let's assume that my lattice now, the atoms form a triangular lattice or a Kagome lattice. So basically my lattices are built of triangles, and that the interactions between the neighbor atoms are in a way that always the spins would like to be antiparallels, okay? So now here is the problem we have. Let's put it up, down, but the third one has a problem. If it goes up, this is going, so in our language, it's going to be energetically very, very expensive. For this one, for this it will be okay. If you put it down, you will have this very energetically expensive. So there is no way that you can build now with this kind of lattices for your materials a nice antiferromagnet. So this was already a problem that had many people thinking about it. One of these basically very important scientists is Phil Anderson, who in fact proposed, in these cases, in fact we have to think about different ways of understanding how the spins are arranging. And he was proposing the concept of spin liquid, in the sense that there is no way that I will find an ordered state. You saw it. I cannot arrange the spins that they order nicely as far as I want it to be in an antiferromagnetic configuration. That's the word spin liquid. Spin liquid, what we mean is that a magnetic state that doesn't order. I can go to very low temperatures and it doesn't order. And the question is, how am I going to define this state? And here's where topology will come in again. So, and let me just show you a way of understanding how these systems are going to arrange the spins. And this is what we call this resonating balance one. Okay, so here, what I want to show you, I put this because, you know, so you know the cat. You know the story of the Schrödinger cat. So whether you can have your cat both alive and dead, and you saw it here, I have good news and bad news, right? So of course you will never have this superposition of a dead and an alive cat, because this is a very, very unstable type of combination, especially. So don't worry, you will never have that. However, in the quantum world, we do have these, basically, these superpositions of different states. They are at work there, and this is in fact the way we're going to solve the problem of the triangular lattice. We're going to make superpositions. So what I'm going to do is what I mean with these. I mean that I'm basically considering a linear combination of having an up, a spin here, and a down here, minus a down here and an up here. You see, so I'm allowing the two possibilities. I'm making a linear combination. So it's like the dead and, so I'm doing the combination of alive and dead, but with spins. And this we can do. In the microscopic world we can do, because these states remain rather coherent. In the macroscopic world this would be so it's a very incoherent situation, and you will never have that. So therefore I'm using here quantum mechanics at its best. And if I do these combinations, I can now, you see, I will make happy, because I can basically, each spin which is neighbor, I'm going to do this type of up down minus down up. So I make everybody happy. There is nobody that is unhappy because the neighbor is down or the neighbor is up. So by doing this, I'm constructing a state that as you see, it has no symmetry. When I was looking at the antiferromagnet, I was following, there was a symmetry, there was a long range order. Here there is no order. And in fact, we know this is not the ground state. So this is not the ground state of the triangular lattice. I need to do, in fact, now I'm going to do even a better job by doing a linear combination of all the possible pairs that I can think of by pairing two nearest neighbor spins. Okay, so this is the state, this is the wave function I was telling you, with which we are going to define how I can describe the ground state, what we call the ground state of these triangular lattice. And now the question is, what kind of state is that? And this is where topology comes in. So in fact, this state has what we call topological order. How do I define the topological order? So let me show it here maybe. So let's assume you take one of these patterns, because it's a linear combination of all these states that I was showing to you. Let me assume that you consider just a line crossing your triangular lattice, and let's just count these pairs. How many do I have? So you will always have either an even or an odd number. So you will have, here we have 2, and then you make the next 0, 2. You can exchange 2 of those, and you will have always either an even or an odd number. So you cannot have something in between. You will never have a 0.5 or 0.3. So you see, I'm going again about having a topological invariant that I can define in terms of the way I define this state. So this is a topological state. So again, topology is helping us to understand this state of matter. But this is not the most interesting part of this kind of state of matter. I'm going to show you where we find it. What is more interesting is that when we now think about doing excitation on this state, you know, you are at the lab. If you just shine light, you can start doing excitations on your system, and yet you look which is the response of your system to this type of shining light or perturbing your system. So one excitation that you are producing in this type of states with topological order is what we call a spin-on. A spin-on, so basically what you can do is you can break a bond, or you can just take one electron out and then you break the pair. What you are producing is here a spin, which is a spin 1/2, but you have no charge. So this is what we are calling it's you build up new quasiparticles. We call it quasiparticles because they cannot survive if you were in vacuum. So in vacuum you could never have a particle that has spin and has no charge. We know which are the particles in vacuum. That's electrons, and then we have quarks, and so this is well defined by particle physics. But you will never have this kind of particle. So this is the beauty of condensed matter, so of quantum materials, that you can realize completely exotic, what we call quasiparticles, because you need the collective of the environment to build up these new quasiparticles. And this is one example. Another example is the Majorana fermions, which were in fact introduced by Ettore Majorana. I'm done. Okay. Just to tell you that this kind of, they have a lot of applications in quantum computing. So just to show you that we do things that have some use. And the last question is, where do we find these quantum states? So this is one of the materials where we find that. We find that the ground state is spin liquid and spin excitations. And the challenge, and here is where I'm sorry, the big challenge that we are discussing nowadays and also in this workshop is the relation between the material and going, so how can I find these states? In which materials I find these states? This is a long way. And this is where we are working on. And thank you very much for your attention.
Now we need questions. There were so few, please.
So the quasiparticle is not a real particle.
No.
It is something that is a function of the things around it, but it, as you say, with the spin on it, it has spin and no charge.
Exactly.
It's really a property of that in local environment.
It's a property of the collective that you have in this system. Yes, alone it will never survive. It needs a collective. Yeah.
So it's the context that determines the state?
It's the context that determines. So it's you see in solid state we work what we call it's a many body problem. So we have many and many particles that are interacting, and it is because they are interacting that they form these states, these quasiparticles, and only in this collective you can find them. If you take out, as you say, if you take your environment, this is not anymore there. So these states are only in the collective.
Is that why you call it emergent?
I call it emergent in the sense, exactly, because if I give you the electrons and you will say, and I say, can you get me such a phase? You will never think about it unless you put them all together and let them interact, right? The interactions through the charge because they have charge, through the spin because they have spin. Yeah.
And one dumb question. So the quasiparticle is quantized. That's why it's a quasiparticle.
Yes, it's quantized, and it's what we call it's a fractional quantization. That's the beauty of it, because I get new particles that have, so I can get particles that are neither fermions nor bosons. So we call it anions. An ion, because you can have particles that have a statistic that are neither one nor the other. That's why it's so rich. Solid state. I'm making propaganda of solid state. I am allowed, right?
You're allowed.
Yes, thank you. So that's why it's such a rich field.
So you're talking about fractional states. Does this have anything to do with fractals?
Fractals, okay. In fact, good that you ask, because now I have some colleagues that work with what they call fractons. So it's good that you ask.
Well, fractional dimensions, it's like 2.5
Yes.
dimensions,
And in fact,
like
they get this word fracton because from looking back in the way this concept of fracton developed, which is also one of these particles, it came in fact from thinking about fractals. Yeah. So good that you asked.
Well,
there are
fractal
fractons.
dimensions. Why not fractal states?
Yes. Of course. Yeah.
I take it from your diagram here. This is the theoretical down here that you're talking about.
Yes.
You have yet to see these states in nature.
Okay. So there are. Let me now tell you a little bit more. In fact, for this material, so what we do in theory, we try to predict if we were to measure now this state, let's say by putting neutrons. So just perturb the system with neutron and look at the response. So this is the way, in fact, we probe these systems, by putting a magnetic field or neutrons or electrons. So by perturbing the system and looking at the response of the system. So if we, by knowing this state, calculate the response, we predict you should see these patterns. Okay, so in experiment they have seen some of these patterns, but it's not completely conclusive. But indeed, for this material, this is one of the most, maybe the one that is being discussed the most, because it seems that the patterns look very much to what you predict if you have such a state.
I assume these would have to be measured at very cold temperatures?
Yes, so they go to 4 Kelvin, 2 Kelvin. So yes, you have to make sure that you are not having a long-range order, so that you remain in this spin liquid state up to very, very low temperatures, because you have to get rid of all the thermal fluctuations, and only the interactions between the electrons are the ones that remain, the spins.
Okay, thank you.
Thank you.